Hello, this is Chenchong from Washington University in St. Louis. We will mainly discuss our study of the plume height effects on atmospheric radiative transfer and further the formation of secondary organic aerosol. Biomass burning is the second largest source behind anthropogenic emissions of the contributors for pollutants in the global troposphere. Particles and gas emitted from these burning events have multiple adverse effects on human health. To investigate the impact of wildfire and biomass smoke on air quality and weather in the continental United States, researchers from different groups conducted the fire influence on regional to global environments and air quality field campaign, FireXAQ in abbreviation, between July the 24th and September the 6th in 2019. To advance our knowledge in fire emission study, in our current modeling study related to FireXAQ, we mainly focus on two aspects of questions. First, we want to answer the question that what is an accurate estimation of the amount of fire emissions, and also how to quantify the effect of the wildfire plume. To properly estimate the direct fire emission, we use the historical vegetation cover tabs data. We will further detail the methodology we used for the estimation of the real-time burned area in the following slides, and also we will show some sensitivity analysis for the plume height effect. Second, we also want to discover the interplay mechanisms between particles' chemical and optical properties. After organic particles have been emitted from wildfire, organic particles, especially those light-absorbing ones, they experience complex evolution for both chemical and optical properties. We conducted the study mentioned above in the last slide within the Wolfram framework. We used the emission source data as the input parameters. We applied this emission together with geographical and meteorological data together into the Wolfram. The volatility basis set, or VBS in abbreviation, which related to secondary organic aerosol formation and radiative transfer modeling, are modified to further study the interplays between photoelectric rate and secondary organic aerosol yield rate. The studied West US FireXAQ domain and the experimental sampling period is shown in this figure. We firstly take a look at those secondary organic aerosol gases precursors from the background biogenic emission. Natural biogenic emission was compiled by the Megan version 2.1. This model provides the emission intensities of the major organic gas species, which can further generate secondary organic aerosol. In this slide, I show the emission intensity map for two dominant types of those gas species, isoprene and monoterpenes. They show that without additional emission source, the level of natural background emission for those organic species are quite low in the FireXAQ region. So if we observe high level of organic aerosols in this regime, it's much likely that they are from additional sources or transported from other areas. The additional source mainly means fire here. Fire will not only significantly contribute to the primary emissions like black carbon, primary organic carbon, carbon monoxide, but also generates organic gas species which can further form particles. So the next question is how to characterize fire emissions. In this study, we used the product of four input parameters to quantify the fire contribution in each pixel. First, above ground biomass density, which gives us the estimation of the vegetation amount in each pixel. Second, combustion factor, which denotes how much of the fraction of the entire vegetation mass can be combusted and converted to combustion products. And third, emission factor for specific combustion products. It quantifies the conversion efficiencies of the biomass to specific emission products. And the last one, the burned area. The first three factors in this formula for different land cover types can be retrieved from previous studies. The last one, real-time burn area, we mainly retrieved from multiple satellite products. The retrieval process will be detailed in the following slide. We tried the MODIS active fire products, including MODIS level 2 products, MOD14 and MYD14, and their processed products. The governing equation of the burn area retrieval are shown in this slide. We used the radiances of two infrared bands on MODIS, L4 for 4 micrometer and L11 for 11 micrometer for active fire pixels, and their adjacent background radiances L4B and L11B as the input parameters as well. Based on this equation, we can calculate the real-time burn area inside certain active fire pixel, which is the product of the fraction P and the MODIS fire pixel area, which is about 1 square kilometers. Based on the equations we introduced above, we can draw a response curve for burn area retrieval. In this plot, x-axis is the brightness temperature of the active fire pixel at 11 micrometer. Y-axis is for 4 micrometer. The background temperature for two bands are fixed as constant at 295 Kelvin and 290 Kelvin. Note here, in practice, the background temperature is not constant at all and should be derived from the MODIS products, which includes fire radiative power information. After we have detected temperature, we have retrieved the exact burn area and the fire temperature from this figure. Previous studies have directly used the original MODIS pixel size 1 square kilometers as the burned area, which can certainly lead to a significant overestimation of the realistic burn area, and furthermore, the fire emission intensity we have mentioned above. So in the FireXAQ campaign scale, the burned area fraction we retrieved are always below 0.1. Our group members have also applied both in situ photoacoustic measurements and the filter-based electron energy loss spectroscopy to measure the refractive index for the light-absorbing organic carbon. They found that these wildfire-emitted organic carbon have high-valued imaginary parts of the refractive index, which implies they may significantly absorb radiation at UV to short visible wavelengths. We applied their observed optical properties for organic carbon to study how the wildfire plume heat influences the radiative transfer in the atmosphere. In this sensitivity analysis, the column or total AOD of organic carbon in the atmosphere is fixed as 1.0 at 550 nanometer. The column AODs at other wavelengths are rescaled and computed based on organic carbon's optical properties. We assume the aerosol in the atmosphere is distributed in an exponential decreasing way. Then the layer AOD and extinction coefficient can be calculated based on the definition of layer thickness and assumed aerosol scale height. In the red figure, we further calculate the radiative effects of the organic carbon based on our atmospheric profile assumption. We firstly define cumulative radiative effect, or CRE in abbreviation, which is the integration of the nadir spectral irradiance along the wavelengths. The nadir spectral irradiance value shown in this figure has already subtracted the irradiance contributed by background atmosphere. When the upper integration limit is infinity, CRE equals to the direct radiative effect of aerosol, which is DRE. Red area shows the CRE when scale height is 20 kilometers. Red plus green shows the CRE when scale height is 5 kilometers, and red plus green plus blue shows the CRE when scale height is 10 kilometers. We find that the scenario which has the largest H value, or in other words, when particles distributed in more balanced way for lower and upper atmosphere, has the lowest CRE values in almost all wavelengths. However, the comparisons of CRE between 5 kilometers and 10 kilometers show some very interesting results that CRE at 10 kilometers have the higher values at the visible to near infrared regime. As the wavelength increases, the difference between CRE at 5 kilometers and 10 kilometers decrease, and if we plot, exceed the current axis limit, which is 1.2 micrometer. We found that CRE at 5 kilometers will finally surpass CRE at 10 kilometers. It implies when more aerosol locates in the boundary layer, it will always lead to larger total direct radiative effect. However, more aerosol exists in the higher troposphere, it will more efficiently increase the aerosol radiative effect at the visible to near infrared regime. So as a summary of this presentation, we have answered the first research question. We used the MODIS satellite data to estimate the real-time burned area. Also, we utilized the optical properties of light-absorbing organic carbon derived from in situ measurements and macroscopic analysis. Together with forward radiative transfer simulations, we studied the effect of the plume height on atmospheric radiative transfer. Our future work is also shown in these slides, and I'm open to questions now.